Hi guys, today I want to go through some facts about power series, okay? And basically uh, also the idea of limits as well. Maybe not too technical, I hope, but these two things should go hand in hand to give an idea of any time I wrote this kind of symbol with n goes 0 to infinity and then goes to 0, so this summation to infinity. Usually in videos about integrals and exponentiation or exponential, I always translate that into a truncated sum or just an actual sum where you can list um, where you can actually list the component of the sum dot, 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 and then f2n, and this is as many as you want but finite. It's of course it's easy to deal, well, not, it doesn't have to be easy, but this is what happens, for example, when you translate this infinite sum in a computer program. You usually have a large, very large, but finite size vector of element n, and then you evaluate your function in of x in all those set of 1, 2, 3 and point, and then you got a sampling. Basically, you think about the sinus, for example, for a moment. You got some points. Um, if you think about the function sampling those points, and then you sum all of them together. Okay, so then the question is, okay, we know how to deal with sum. We can do products. We can do um, differentiation. Divisions. Also differentiation, of course, integration. But what happens when we need to go to infinity? And second of all, why we need to go to infinity and what does that mean? Okay, so let's start from something, so a simple example. So suppose, so what is the limit of a function? So usually a limit of a function is defined as following, which is a bit abstract, but I will give you also a graphic representation. Suppose you, and it's by the way it's written like this. So you have the limit for the variable x, so you're evaluating an x around x0. So for example, you have your function, which could be any function. In this case, let's pick sinus. Okay, and then we have got x0, which is this point here, which can correspond to, for example, 1. Okay, but let's be this is an easy one because we know that x0 will be pi over 2 in this case, but so we know the number of it. But what does that mean actually? This means that in this case is exactly f of x 0, because we know the function in this position. So if we limit means that if we move away from x0, okay, we are collecting numbers that are around 1, but not quite, right? But as you can see, the more you move towards x0, let me do a bigger picture. So it's a bit squashed on the corner, and I need a larger graph to explain what I want to say. Okay, so we have got our x, our y as usual. This is the real numbers, not complex. You can do limiting complex plane as well, but at the moment I'm just considering real number. So okay, we don't know what it is. Let's say we don't know, even just to start with, we don't know what it is. But what does this mean is that if you move away from x0, so you have these points here, for example, all of these points correspond to values that, as you can see, are going close to 0. And I will draw the other one in a different color. Let's say blue, and let's say purple. Oh, purple. Yeah. As you can see, these points here are touching the line somewhere, and then go to the y-axis. But they are, as you can see, well, the correct term is converging, but they are moving towards this point here, which we don't know what it is. It's the limit. So basically, what I'm saying is that the process of limit is a concept that says you have to, first of all, you have to pick, usually, formally, you have to pick a number epsilon. No, so you have to pick a number d, a distance that you choose. So you set a boundary around your x0, and this distance is d. And then you have to say that for each point which is around the distance x minus d0 d over 2, x0 plus d over 2. So you're saying you pick any point around x0, okay, any point around within a certain amount of length. In this case is d, which can be arbitrary. You choose it as close as you like or as large as you like. It doesn't matter. Of course, the idea is to go close to x0 to be, let's say, more accurate for certain function. But the idea is to as close as you go to the x0 point with your other element. The idea is that what happens if the limit exists is the following: is that, and let me write it up here, if the limit exists, which may not exist because this condition may be not satisfied, you want to have that f of x0 minus f of x, and let's call them n, the distance, so the absolute value, positive or negative, it doesn't matter, has to be less or equal than epsilon. Epsilon is a small value. Epsilon is a small value, as small as you want. So epsilon as small as you want. And this is key. So for any epsilon, there must be, so for any choice of d, there must be an epsilon here that tells you that if your sequence of point x of n, so x of 1, x of 2, dot, 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 x of n, whatever, that are inside this small set around x0 for all of the point, it must be that there is an epsilon after which the difference between your points and x0 is always smaller than this epsilon here. Okay, this should give you the idea that basically essentially what happens is that you are getting closer and closer to the value of f of 0, and the difference of this number, it's finite, is close to 0, the difference. So you want, so in other terms, you can think about epsilon as 0, and you're saying that the points accumulate around f of x0. Okay, now of course if you have a function well behaved, let's say, meaning that you know the value of the function. Let's do some simple examples. So if you know another function, let's pick an easy function, and the function is x squared. Okay, f of x is x squared, and this function here. So what's the limit of f of x for x goes to 2? Okay, so I'm asking what's the limit of this function. In this case, since we can place, so the first thing that you need to do usually with the limit is to check whether you can replace x by the limit point. If you can, without trouble, you just substitute it, and then you get your limit value. And this happens for well-behaved function, for example, if they don't have gaps, or if they are easy to calculate. And then I will tell you, and in this case f of x is 4 f of x, f of 2, because 2 to the power of 2 is 4. You don't need to do any calculation to do that. You know that because you know the value of the function. Now, there are functions which are a bit more complicated to calculate the limit of. Doesn't matter if I give you an example now. Maybe I will give some in the reference. But there are, I mean, I don't want to go in the details of how to calculate the limits. There are many theorems that we have to, well, not many, some theorems that we should know how to use to evaluate limits. Sometimes it gets a bit technical, and I think it's a bit, not boring, but it's not what I want to say. What I want to give you is an idea of what a limit is, and I will give you another example where this idea, let's say, give a different result, which is not something that you would encounter, let's say, well-behaved function. But the other thing that I want to say is give you a graphical example. So suppose that these are n, the values of the element around, so x minus x0 is less than d, we said. So for all the value inside this x minus 0, we have a list of elements that goes from 1 to infinity. Let's call them n. And what happens, this is the value of the function in those points. Okay, and what if the limit exists? What I'm trying to say is that when you evaluate the function on these points, you can have many values, random values. We don't know what those values are, but eventually, if the limit exists, they will all bunch towards 0. Okay, they can go, I mean, we put an absolute value, so we are above 0. But what I'm saying is that in the long terms, they will all go to 0. So there won't be differences after a certain number, whatever number it is that you choose, that you find. That depends on the choice of d. You will find an epsilon, so you will find a value for which the difference of your function against those numbers is less than epsilon. So it goes to 0, basically, what you're saying. There are some functions that do not have limits, for which this doesn't happen. For example, an easy example is again, no, let's do a not super easy example, because I don't want to go limit to infinity, let's say like x squared. For example, I mean, just to say that x squared, when you go to infinity, it goes to infinity as well. But that's a different, I mean, it's still a limit, but it's not what I want to talk about, which is different. So suppose you have 1 over x minus x0, this function here. Okay, now we don't know what x0 is. I'm not going to do the plot, which by the way is easy to draw, so let's do it. But so what I want to say is that what happens when you try to do the limit of this function when x exactly goes, no, let's put a number here, 2, to be precise, and that x0 is 2. What happens when x goes close to 2? So you have to pick your d, distance around 2, and then you pick your values around 2, how many you want, infinitely many. The more you're close to 2, you will get some values, and I'm going to draw now in a sec, and then you should get some value in the y-axis, your f of x. But here's the thing: when you go close to 2, x minus 2 is basically 0. Okay, because if you replace, for example, 2 on your function, 2 minus 2 is exactly 0. Meaning that if you're walking closer to 2 in this fashion here, you are approaching 0. But 1 over 0, we all know that 1 over 0 goes to infinity. So in this point, the function goes to infinity. And actually, it goes to infinity in this way. And then it goes to infinity in this way here. Okay, in that sense, you cannot find an epsilon. In this case, there is no epsilon for which the difference of your function minus the points that you are drawing in orange here, so the point that you choose, there is no way to be small. Actually, it's getting larger and larger the closer you go to 2. So this is a very simple example of a function that doesn't have a limit for x equal to 2. All the other points are fine. You can find the limit to that, but for x equal to 2 you can't. And this is saying that the function diverges to infinity in this case. Okay, so and this was 1 over x minus 2 is it's not a crazy function. It's not something uncommon. I mean, you can find it in many scenarios. But for example, one other function that you might have heard about, which is other two functions I want to give you, which do have a divergence, so they don't have a limit for certain values. So I want to give you an interesting function, which is log x, any log, any base, it doesn't matter. I'm thinking about base e. So log x is that function for which if you do log x of e of our exponential, it gives exactly x. So the base of log is the logarithm, is the Neper number, the one that we all know, sum to infinity n equals 2 over n squared. This guy, we already encountered it. So log x is that function. This is the inverse function of your exponential function. So as you might remember, so the exponential, so the log, first of all, how do we draw the log? The log is basically, if you remember, you can rotate the exponential graph from x to y. So if you look it from the other way around, this is exactly an exponential function. But in this case, as we did for the parabola at some point, if you remember the square root, we rotate the function this way, and then we had to choose which one of the two branches to pick, and then we got our square root of 2, which was only defined for positive number, okay, and not for negative. If you remember, this part doesn't exist basically. Same here for the logarithm. The logarithm doesn't exist for negative value, at least not in the real numbers. In the complex number it does. We're not going to go into details now. Maybe we will in another video. But what I want to say is that what happens to 0. So I hope I didn't draw it. Should be fine. So what happens to 0 is that this function still go to minus infinity, and this makes sense because, so let me write it this way. Oh, I lost a pen. Oh, okay, sorry guys, I'm a bit. So if we do log, what's the limit? I want to do the limit of logarithm of x. What is this number? Okay, so another way to think about the logarithm to answer this question, the logarithm of a number n is that number that you have to use to raise the base of the logarithm, so e to the n equal to x. So those two are the exact same definition. When you have the logarithm of a number x gives you n, it means that you can use n and raise the base of the logarithm, e in this case, to the n power to get this value of x. Okay, this is okay, and also of course there is a, I will tell you that there is a power series of the logarithm, but I will go in the next slide. So let me finish this two function and then I will switch to the power series. But what is when the logarithm has to go to 0, so think about e to the x. What must happen to x in order to go to 0? In order for e to the x to go to 0, well, x needs to go to minus infinity because you have e to the minus large n. It means 1 over e to the n. E to the n is as large as we want. 1 divided by a number as large as we want goes to infinity. Exactly. So we need to go. So basically, the function goes to minus infinity here. And this is a way to say that there is nothing that you can do to overcome the zero. There is no minus logarithm of minus x. And it's a way to say that this limit, there is no epsilon in this case that can let you approximate logarithm of x around zero well enough, because it diverges. So exactly, so if you think about the limit is another way to approximate your function. So you can say around the value of x, we got roughly our f of xn, and the difference between the target value and f of xn is about epsilon. So you have two approximations on the y and the x-axis to get your number. Well, the other function that I want to stress or highlight, so we talked about sinus and cosinus. We all know that they have these nice two complementary graphs. I call them complementary in a strange way, in the sense that one is the same as the other, just shifted by half of a period. Okay, exactly, but they look the same if you look closely. Well, if you look carefully, they are the same. It's just they move one respect to the other in that direction. Okay, but then what about sinus of x over cosinus of x? We said that we can, when we have a power series, we can do, this is called tangent of x. Of course, sometimes cosinus, or sinus by the way, but in this case we're doing the tangent, the cosinus, which is the blue line, goes to zero here, for example. Here, for example. And I drew it incorrectly, because this should be minus pi. Exactly. Here, for example, in pi over 2. And in this point, sinus is exactly 1, but the cosinus is 0. So we've got 1 over 0 again. If we put the limit of the tan fx goes to pi over 2 of tangent of x, we've got 1 over 0, which again goes to infinity. So the graph of a tangent, for example, is, and by the way, here goes to infinity and here goes to minus infinity, because the sinus is plus or minus. So if you draw the tangent, which I'm going to do now, in those 2 points, in 0 is infinity, and then it goes to minus infinity in pi over 2, something like this. And then it repeats every time. Okay? What I'm saying is that in these 2 points, 0 and pi over 2, there is no way that you can approximate the function. All the other points you can, because you can do, look, you can just take the graph, took a small d, and then you have an epsilon, which are the boundaries, if you like, of this. And then you have your epsilon here. You can approximate a function, a point around any number, but not when it's pi over 2, or repeatedly pi over 2, and 0, for example. Goes to infinity. So you cannot do that. Okay, so I hope that's at least an idea of what is a limit and how to, not how to use it, but what it does and what it means. Now I stop the video, and then I will talk about power series as we said at the beginning. So see you soon.